Hello, my name is Gedalia Knizhnik, and I'm presenting the paper I wrote with Dr. Mark Yim for IROS 2021 titled Thrust Direction Control of an Underactuated Oscillating Swimming Robot. In this paper, we discuss a new controller for our single motor robot that drastically improves swimming performance. The oscillating swimming robot we use is called the ModBoat. This is a single motor swimmer that uses conservation of momentum and two passive flippers to propel itself and turn. You can see the core propulsion mechanism in this video here. The motor spins the bottom body relative to the more massive top body, and the oscillation causes the two flippers to open in a paddling sequence. Modifying the oscillation parameters allows the paddles to create both propulsion and steering. In previous work, we demonstrated that pausing at the peaks or troughs of the oscillation creates effective inertial turning. This can be synthesized into a controller, which can achieve effective waypoint tracking as demonstrated by the blue path on the plot on the right. The red line represents differential thrust, the previous best control method for this type of robot, which modulates the frequency of oscillation to cause one paddle to thrust harder than the other. The unique encapsulation of the ModBoat allows it to dock together and form modular reconfigurable structures. Prior reconfigurable surface swimmers, such as the TEMP system shown here on the left, have required holonomic actuation and are therefore limited by the high cost of individual modules. ModBoats have only one motor rather than four, which makes them inherently less expensive, but the control problem becomes far more challenging without holonomic actuation. We have been able to demonstrate docking for ModBoats in prior work, and an example of such a maneuver is shown in this video on the right. But docking under current methodologies requires convoluted strategies to compensate for insufficient control, which we would like to avoid, and suffers from limited precision, which we would like to improve. So we have two methods that work at varying levels of effectiveness to control ModBoat modules, but both methods have significant weaknesses that make it difficult to move forward with them. Differential thrust, which shows poor waypoint tracking performance, suffers from very low control authority. But on the bright side, the oscillation cycles have a constant length, so planning can compensate somewhat. Inertial control, on the other hand, has very high control authority. But because the control variable is time, path planning becomes incredibly difficult. What we need is a controller that combines the benefit of these two methods, one that has high control authority, but also a constant cycle time. Such a control method can be found in other robots that use similar propulsion methods. Generally, these are set up as foils, with an internal rotor that provides angular impulse, and then the foil generates vortices that turn this into propulsion. The figures here are two examples of such fish robots. These robots have shown success with using a variety of torque-based continuous feedback laws that track velocity and an average heading. Although the ModBoat's propulsion mechanism is different, flippers rather than a foil, there is reason to think that the same control strategy would work. A critical difference needs to be noted, however. The foil-shaped robots rely heavily on a no-slip condition at the tip for their dynamics. Although the ModBoats have a foil-shaped tail, its thickness is negligible, and so no non-slip condition can be applied. This will have important ramifications later on. Shown here are the dynamics for the orientation of the ModBoat, with the angle theta being the tail orientation and phi being the motor angle. We have some quadratic and linear drag terms and conservation of momentum between the bodies contributing to motion here. The translation equations are omitted, but oscillations of the motor will produce force along the center line of the tail orientation on average. Let's say that we apply a control law of this form, with phi double dot in the first equation, given by tau in the second. The control law applies a sinusoidal torque, as well as a proportional term based on the difference from a given reference heading. Rearranging somewhat, and substituting psi equals theta minus theta r, we arrive at the following equation, where d combines the drag terms. This turns out to be the equation of a damped nonlinear pendulum, which we know can be forced to swing around its down direction. Since the down direction is defined by the reference heading theta r, we can point the oscillations in any direction, and hence the thrust vector. Although the control law has three constants, beta, k, and omega, this pendulum perspective demonstrates that there are really only two. For best results, the pendulum should be forced around its natural frequency, which is influenced by beta. Since in practice, I sub t is much greater than I sub b, we let beta just equal omega squared. This leaves two knobs. Omega determines the frequency of oscillation, and hence the responsiveness of the controller. On top of that, k loosely controls the amplitude of oscillation, and therefore the swim velocity. We can simulate the resulting equations of motion and find pretty nice behavior. The tail angle oscillates around the desired heading and responds within 1 to 2 seconds to a step change in the reference value. This is very promising for using this controller for single module control. Now we come to the ramifications of the lack of no-slip condition I mentioned earlier. A no-slip condition has the effect of forcing the thrust direction to equal the direction of travel. Without it, controlling thrust alone is insufficient. In this plot, we see that play out. The mod boat is tracking a reference heading of 0, going to the right, but around the 1 meter mark, I give it an upward shove. As you can see, the resulting trajectory is nowhere near the desired direction, because although we continue to thrust to the right, we're still drifting up. The trajectory would settle eventually, but we don't have that kind of space or time. We can compensate for this effect by adding a travel direction layer to the controller. Instead of commanding the desired direction, we use it as a feed-forward term in a proportional controller. The second term here considers the difference between the desired and observed travel direction, calculated as shown, and uses it as a vector error term in determining the actual commanded reference heading. You can see the major difference in the orange trajectory. As soon as the disturbance is applied around the 1 meter mark, the thrust vector swings down to cancel out the observed upwards velocity, returning the travel direction to the desired value. We're able to apply multiple disturbances, and the velocity recovers quickly in both time and space. Once this additional control layer is added, it turns out that lacking a no-slip condition has the effect of significantly increasing maneuverability, since we need very little distance to change the thrust direction. Here's some trajectories comparing the thrust direction controller in blue with the prior best inertial controller in red. For the 1 meter square on the left, we see sharper corners and straighter line segments, and the new controller can even execute a ½ meter square, which is 3.3 body lengths for reference. We see the same effect when executing linear trajectories, as shown on the right, where we get much sharper and shorter turns. The inertial controller also shows significant deviation from the straight line on the return trajectory, which the thrust direction controller does not. One last thing to note in this comparison is that the waypoints shown here are 0.1 meters in radius, but the inertial controller tests had waypoints 0.2 meters in radius. So the thrust direction controller actually has much less warning about the incoming turn, but still does much better when performance is considered. The biggest problem left with this control method is the canonical saturation problem. The top body is essentially functioning as a reaction wheel in this setup, and when the reference heading changes, we get unbalanced torques. The top body thus spins faster and faster, losing control authority as it goes. How could we possibly deal with this? The solution is to leverage cyclic orientation. A left turn by pi/2 radians is equivalent to a right turn by 3 pi/2, but has the opposite transient effect on the actuator. Smart choices of reference heading can therefore keep the angular velocity bounded. The issue is that the controller, as written, cannot distinguish between equivalent angles. So we introduce a desaturation term as shown. We compare the angular difference to its value when wrapped to minus pi to pi, and this differentiates between equivalent angles. This has the effect of overruling the sinusoidal tracking term until we are in range of the desired value, at which point it reduces to the original controller. This works fantastically well. Here's a sample test, where we command an initial swim direction for 15 seconds, and then step it by either pi/2 or minus 3 pi/2. Both represent the same final direction, but result in drastically different angular velocity profiles for the top body. So we can't drive the angular velocity to zero, but we can keep it bounded, which will allow us to maintain higher levels of control authority. There is a minor cost to the trajectory when a non-standard heading is used, but it is negligible in the long run. To minimize it, however, we only activate the desaturation by either adding or subtracting 2 pi to the normal reference heading when the reference heading is already changing due to a new waypoint, and also only when the change would not already lower the velocity by its natural direction. This new desaturated thrust direction controller does even better than the regular thrust direction controller. The trajectories are straighter and the turns are sharper, and we certainly outperform our own prior methods, inertial control and differential thrust. And this comes down to the increased control authority the desaturation term earns for us. The little wiggles you can see in waypoint 4 are the trajectory artifacts generated by the desaturation events, which are very minor on the scale of the desired trajectory. As I mentioned on the last slide, because of these effects, we choose to only apply the desaturation term at a waypoint transition, when the trajectory would be affected anyways. Here, you can see the modboat executing the 1 meter square trajectory under the desaturated thrust direction controller. The overlaid waypoints are only approximate, but the trajectory is clear. Relatively straight line segments with sharp turns characterize the performance. You can again see the desaturation maneuver occur at the bottom right waypoint. The mod mode moves back slightly as the actuator desaturates, but the effect on the overall trajectory is quite minimal. Performance similarly improves when we look at linear trajectories. We get a small artifact due to the desaturation term, but the turn is sharp and quick, and the segments are very straight. One last thing to highlight is that the improved performance of this controller allows another maneuver. Simply by commanding a single waypoint, the modboat can station keep to within just over 1 body length. This is impressive considering that the system has only one motor and cannot actively control its paddles. Of course, more intelligent methods for station keeping could probably improve performance, but even this naive approach shows great promise for the system. Neither of our previous control methods could effectively station keep. Thank you for watching this presentation, and please reach out with any questions or comments.